I think you are the only one not to know that I have spent the last 4.5 years of my life between Copenhagen and Melbourne, because there was an international collaboration between the University of Copenhagen and the CSIR on Marine and Atmospheric Research in the frame of a big project that basically focused on the last deep drilling in Greenland, which was called NEAM. And I'll tell you in a second. Basically, I'm talking to you, basically. I'll explain in a second why NEAM. So basically, this talk is about the two major papers we published. And the first one I will talk about is the one that is basically comprehensive of the whole field campaign that went on from 2008 to 2012 in the northwest part of the Greenland ice sheet. We had a deep drilling organized by the University of Copenhagen and a couple of shallow drilling, which were basically done in 2008-2009. And I personally took part at the expedition in 2009 to sample the firn, and I'll tell you in a while about the firn. Okay, sorry, I forgot. Why NEAM? Because North Greenland, Eemian ice drilling. The project focused on this geological period, the Eemian. What is the Eemian? The Eemian is a period that goes between 130,000 and 115,000 years ago, and it was the last interglacial before the present one. So as you can see, on the right y-axis, the temperature anomaly in the last 800,000 years, we had big oscillation in the temperature between warm periods that are called interglacial, this is the peaks, and cold periods that are called glacials. Okay, so the period, okay, the cyclicity is about 100,000 years. Now, we are now in the period called Holocene, which is an interglacial, so it's a warm period. The last interglacial, so the last warm period, was more or less under 20,000 years ago. The last warm period is called Eemian, and has got very interesting characteristics in terms of temperature, as well as dynamics of the ice sheet in Greenland and in Antarctica. Because being the temperature so high in the last Eemian, in the last interglacial, it can be used as an analog for future conditions with high temperature, but without any anthropogenic influence, significant, actually non-anthropogenic influence at all. Okay, so the focus was on this specific period, and basically what we did, we went up to North Greenland, and we sampled a deep ice core, which went down to almost 2,500 meters. Right? So this is the drilling we used to go down 2,500. No, I'm joking. You can't go down 2,500 meters with this one. Of course, this was just a shallow one. You need much more sophisticated stuff to go down 2,500 meters. And you need a drill which is something like 4 meters. It's a big drill. And it's computer automatically operated. And every time you go down, depending where you are, it takes 10 to half an hour, 10 minutes to half an hour to basically go down 1,000, 2,000 meters. And then every time you get something like 1, 2, if you're lucky, a bit more than 2 meters ice core. So it took almost 5 years to basically drill down to 2,500 meters, the whole core. And finally you get to the bottom, and you also drill some rock in the ice. Let's be clear, this is not our major aim, it's not our objective. This was, they were happy just because having reached the bottom of it, then the sampling campaign was over and they could go back to Copenhagen and rest. Okay, so I told you 14 nations collaborating to the same project, at the same project. Lots of measurements. This is just a small subset of all the measurements they've done, but it's very representative of what we got out of this sampling campaign. So remember, the focus was last interglacial, very high temperature. Let's see what was the response of the ice sheet in Greenland to that very high temperature. So some people used to think that Greenland was completely free of ice. Some other people were not sure about it. So there was a dispute going on. So this is what we got in terms of delta 18 of ice, which is the proxy for the condensation temperature in the ice. So that tells you something about the temperature variation in the past. We got some gases, concentration of trace gases like CH4, methane, N2O. We got the 18 of oxygen in the atmosphere. We got the 15N of N2 in the atmosphere, and the air content. Okay? So all of these are...
I'm a little bit lost with the horizontal scale.
Yeah.
Below we have the NEM, and up is the another chord.
Okay, so yeah, I'm just getting there.
Sorry.
Okay, so this is in NEM, for NEM, this is the last 300 meters. Okay? So the first thing that we need to note here is that the delta 18 of the ice, which is the proxy for the temperature, the condensation temperature in the ice, so related somehow to the temperature in the past, has some disruptions. Okay? So that means that somehow the ice does not have a continuous stratigraphy, and the chronology must be somehow related to that problems. So you can see that there are jumps. There is no continuous record that you can, so there must be some problem there with the stratigraphy, the chronology, right? And that's why it's not so easy to relate the depth scale to a age scale, right? So you have to convert to be sure that one of these periods correspond to in the last interglacial 120,000 years ago. You have to convert the depth into an age scale, right? How do you do that? It's not that easy, unfortunately. So you have to compare. Normally what you do, you have a previous ice core drilled somewhere else, and you have a chronology developed for that ice core, and you compare your new ice core to the previous one. And you say, okay, this corresponds to this corresponds to this, so we have a matching, kind of wiggle matching.
So what do you compare? What do you...
For example, what you can compare is globally homogeneous parameters, such as the delta 18 of oxygen. This is one thing that you can compare, because that shouldn't change going from one side to another, one location to another, right?
Of oxygen in water or oxygen?
Now this is oxygen in the atmosphere, so O2. So what we did, we compared the NEM scale to the grip, and grip up there is another core that was sampled a few years ago. And so it was very important for us to compare this scale to that scale and match the chronology. However, the first question we need to ask is, why is the stratigraphy disrupted? Okay? And so, different type of measurements had to understand that. Basically, this is basically a radar, right? It's what you can do also in solids. So what you can see is that the ice layers, you can see all the layering, because of the different properties in rheology, so the different, how the ice deform because of the movement of the ice on the surface of the rocks. Basically, what you can see is that the layers of ice have folded, have turned and folded. So basically what you can see is that if you drill here, you don't have a continuous chronology stratigraphy of the ice. And this is basically mostly because glacial ice, which is the one up there, deforms very easily, while the interglacial ice remains more rigid. So there is a difference in the deformation of the two ice. The interglacial has got very different rheology, so different granulometry and so on, whereas the glacial ice deforms more easily. And so that creates this upturning and and folding of the ice. So what you have to do, you have to reconstruct that climate record based on what the properties that you know. Okay, and what you see, you acknowledge that there is a huge important peak in the delta 18O, which again is the condensation, the proxy for the condensation temperature. So somehow that should correspond to a warm period, because the delta 18O of the ice is very positive. And you also note that there are very significant spikes in the gases, as well as a decrease. This is inverse, the scale here is inverse, so a decrease in the air content. So this would suggest that there is some kind of surface melting at that stage. So it all points towards this period here, basically the red, being the last interglacial, because to have high condensation, high temperature and very significant surface warming, it means that lots of heat was there during that period. So basically you can identify that as the last interglacial and match other globally homogeneous signals, like, as I said before, the delta 18O of O2 in the atmosphere. So you can match this red curve to the dark gray here, which is from Antarctica, as you can see. And now you see that all the other kind of overlap nicely between different coasts. Nordgrip in Greenland, EDML Antarctica, and our new NEAM, which is the red, the yellow, and the green and the blue points. So basically NEAM has got, there is a missing stage here, but there is a complete record of the last interglacial. So that's what we wanted to focus on, and that's what we got. So this is very important, because now we can go in more details there and study what happened during that warm period and understand how the Greenland ice sheet responded to the warm period. And so, for example, you can see that there was an increase in the 59 N2, in the atmosphere. Again, this is related to how warm the site is, because molecules like N2 diffuse in the firm, and I will show you in the second part of the talk why and how. And if the temperature changes significantly, then you can see shifts in the isotopic composition of N2 as well. You can also see something that is well known in the literature. I told you that everything overlaps nicely between Antarctica and NEAM or Nordgrip, which is Greenland. But, for example, there is a significant difference there. And this is something that is well known. It's related to the inter-hemispheric heat redistribution, but in the Atlantic meridional on the turning circulation. So this is related somehow to how the ocean redistribute the heat over the globe. And basically, the fact that they diverge, it means that in some periods of time, while Antarctica was warming up, Greenland was cooling down, and vice versa. That's why it's called the seesaw, because it acts like a seesaw. The heat exchange acts like a seesaw. And finally, we can reconstruct the elevation change of the Greenland ice sheet. So first of all, how do we reconstruct that? You can reconstruct the elevation change of the ice sheet from the air content. Why? Well, this is quite simple actually, because the more elevated the side is, the less the pressure, atmospheric pressure, and less air in the bubbles gets trapped. So basically, higher air content means that there is less ice, because the elevation of, it's like when you go up the mountain, there is less, the atmospheric pressure decreases. So basically, if the ice was going down, then the atmospheric pressure in the bubbles would increase, and there was more air content in the bubbles. So this is a measure of your altitude, basically. Right? So what you can see is that between 128,000 years ago and today, there is a difference of 200 meters of elevation at the site where the ice was deposited. So there's something you should know. The ice sheet is not something that stays there forever. Actually, it's quite dynamic. And so, if 130,000 years ago, the snow fell there, then we would find 130 years after that, we would find the same snow down there, maybe. And that's what they had to reconstruct with some ice sheet modeling. There is also lots of modeling behind all this stuff that I'm showing you. And so what they reconstructed basically is that our drilling site is here today, 0. 130,000 years ago, it was actually there. Okay, so when we say there was a difference of 200 meters between this point 130,000 years ago and now, we are talking about this point, not this point, right? So what was the altitude at that point in time at that location? And second, very important, from the delta 18 of the ice, of the water in ice, you can see that there is a difference in temperature of 8 degrees. So 126,000 years ago, the temperature was 8 degrees warmer than the mean of the last millennium. So it was a lot warmer than it is now. What happens then to the Greenland ice sheet? Okay, was the Greenland ice sheet still there? Yes, it was, because we found ice. What was the altitude? So what was the mass of ice on the Greenland? Well, you can see, doing some more modeling, that there was a difference in elevation from 128 kiloyears to 122 kiloyears before present. The ice sheet decreased of between 210 and 130 meters below the present one. So basically, what we are saying is that all these measurements suggest that there was a moderate ice thickness change of only 400 meters. You can say, well, 400 meters could be significant. 400 meters is not that much if you compare. First of all, you have to think about these data are derived from our deep drilling at mean, but also the model of ice sheet dynamics. So how the ice sheet moves and flows can be constrained by a number of drilling that has been done in the last 20, 30 years. So there is some constraint there, even if I don't think it's very much constrained. This is just a bit of speculation there. But there are modeling and they are constrained with a number of sites that have been drilled. But the point is, if you translate that in change in sea level, right? This translates into a quite modest contribution to the, say, on average 6 meters sea level change. So we know that during the last interglaciation, when it was so warm, the sea rose of around 6 meters. But according to our calculation, only 2 meters of those 6 meters were coming from Greenland. So where is the rest coming from? And this is just speculation, of course. But if Greenland wasn't contributing that much, then it should be Antarctica. And if it's Antarctica to give more than half of that sea level rise, then it's bad news. Because normally people assume that Antarctica is much more resilient to changing temperature. Whereas here, what we said, guys, this is not very resistant to the temperature increase during the last interglaciation. So there is good news for Greenland. Greenland seems to be more stable than previously thought. It's bad news for Antarctica. Probably Antarctica was giving much more contribution. Okay, I think I will stop here. We can have some biscuits for 3-4 minutes, and then we go to the second class.
Can you, before going to the biscuits,
yes,
can you go back to the second slide where you had the
second,
just the beginning, where you had the beginning of the slide? Yeah, that one. Just to understand better the colors and the meaning of lines and points. The green is the grip core. The light green.
Yeah.
Light
green.
This is grip.
Yeah.
The blue, the dark blue on
all the colored one mean the one the last one. They are all the same.
The gray is
whatever is the color.
Yeah. But it's different. They're being divided in different.
No, I don't understand the difference between there are some spots, some points, and continuous curves. This is just a matter of For example, we have a part which are lines,
Yeah.
and on top of that there are some.
So the points identify the disruption.
Ah. So the experimental data are
The points
let's say
identify
lines.
the disruption. Normally, in a normal, if the chronology, the stratigraphy was continuous, you shouldn't say that jump going from the green.
Yeah, yeah. I mean, but the square and the diamonds are just
Just to
not
identify the
experimental
disruption.
points, are
There's nothing
marks.
special. Yeah.
Okay, this was a little bit confusing for me. They were not experimental points, those. Okay, okay, good.
And in the graph, you use the delta 18O from ice to determine temperature.
Yes.
You use the air container to determine the elevation
Yes.
of the ice surface, and all the other proxies are just for matching it to the other ice core from Antarctica.
No. What you do normally, there are a number of, as I said, globally homogeneous parameters that you can compare. Some others that you can't compare. For example, CH4 methane, you can compare because normally you see shifts, even though there is an interhemispheric gradient. When there is a shift in the northern hemisphere, there is a corresponding shift in the southern hemisphere, so you can wiggle match kind of. The same for delta 18 or 2. There are others that you can, but some others are not the same.
But
For
then-
example,
What did you use the nitrogen and the delta 15 for?
so this one I showed before. It's used to show that the decrease here is telling you that there was actually an increase in the temperature, because in the firn, the delta 15N is enriched due to some diffusion and gravity, and that depends on the temperature. So if the temperature changes, then the delta 15N changes too. N2 is a very stable molecule in the atmosphere, we all know that, right? And the delta 15N of N2 is actually used as a standard. It's so stable that people just go in the atmosphere, same volume can use as a standard of delta 15N measurements, right? But here, it changes. In the bubbles, in the ice, so in the air, trapped in the ice. It shouldn't, because in the atmosphere, we are pretty sure that it doesn't change. So why did it change? It changes because in the ice, in the bubbles, there is some diffusion sometimes in the shallowest part of the ice sheet, and that diffusion is somehow related to the temperature. So changes in temperature affect the delta 15N of N2 in the bubbles in the ice.
But then I don't understand, because then you would expect changes in delta 18 over ice and changes in your delta 15N
Yeah.
to show similar behavior.
No, not similar, because it's different process, completely different process. But they change. In the red part, they change. And they change according to what we know, believe me. Guys, I didn't
Because
show all.
What I see for delta 18O from ice, it goes up and it goes down. But if you look at delta 15N during the Indian, it just seems to go up.
Yeah, it's a completely different process. You have to go into the details. There are lots of correction there, especially there. It's a completely different process. I don't know. I can't explain actually all the details because I haven't never worked with it. But it would take a while to explain. So let's not go there.
Okay.
What I cannot understand, you match the chronologies, and the uncertainty that you can calculate is just in that direction, or is also
There are uncertainties everywhere, but
I cannot see from
there. Yeah, no. But basically, look at the final numbers. 400 meters plus minus 350. Temperature 8 degrees plus minus 4, so it's big uncertainties, of course.
That's why, and it's only, for me it's really difficult to see only in that direction. You know, the period that you match, it's really short. How you know that it's exactly that?
Well, in depth is actually $50 meters. It's not that short, 50 meters of ice. It's not that short. It depends what you are talking about. There are bigger sectors, but matching big signals like this, it's not impossible. The difficult part was understanding why there was these disruptions, and that's why the title of the paper was doesn't go back. Mean community members, mean interglacial reconstructed from a green formed in ice core. They put it in the title.
But what do you mean? That if we go again there and we core in just
Yeah.
15 meters you can find a different
Another 5
profile
years.
and a
Yes.
different folder.
That would
Yeah.
take another 5 years. No?
Yeah.
Yeah.
Because if I understood well, it's like a single core,
Yes, yes.
right? It's
Look at that. This is where they drill. Okay. If you had drilled here,
Yeah, with a completely different
you
history.
wouldn't probably see anything. And that's why actually radars are so helpful before sintering, because they can suggest where to sinter. Probably the best part is here or somewhere.
Yeah.
You know what I mean? This is a breakthrough actually.
Mm.
The radio echo sounding, it's a breakthrough. And it's the first time they published this kind of results. Nobody has done that before, and it could be really helpful. You could save millions of dollars, because you're drilling this in the good spot. Do you want the distance or not?
Yes, we do, but we have time.
No, we don't have much time. 25 minutes
Let me
really
ask
fast.
another question. The end grip and the in core are how long apart? How far are they? Geographically?
Yeah. No grip?
Yeah.
Means.
Ah.
These are not all of them, but most of them. Most of the cores of the points you see here are basically most of the cores that have been drilled in Greenland over the last 30 years or so. So there are constraints. It's not totally constraining, of course, but there are some constraints. When you run, ice sheet modeling,
What you are telling us is only a part of the history, I guess, because you have a long course, you have like such data, and you are presenting us just a short part.
sure.
I hope
This
that-
is just because we wanted to focus on the
Then-
integration.
but you are in something else with the
But then
rest.
you have 1,500 meters of code that you can use to study all the rest that has already been started. There is an important part that I didn't say. The last interglacials has been already drilled in Antarctica many times. Antarctica goes 800,000 more, back in almost 1 million. They're looking for the 1 million core now. Greenland doesn't. Greenland goes back up to here. However, Greenland is much higher resolution, so it's no small. So you have, instead of few centimeter each 100,000 years, you have that much ice. So you can do more analysis. It's better preserved and everything. So it's here you have already a complete record of the last 800,000 years, but you don't know much about the specific period in time which covered the last interglacial, because it's not high resolution enough in Antarctica, whereas Greenland is. But we were not sure we would get that ice, because Greenland probably before that was completely melted. It was free. The big paper with all the nations collaborating. This is mine. This is what I did in the last 4 years in Australia. And it's basically a collaboration as well, international collaboration, but most of the measurements were done in our lab in Australia, even though the samples were sampled by different people in Antarctica. Okay, so it's about bubbles. Professor Donovan Terasi and some other people know already about this, but I will tell you something extra insight at the end. It's about bubbles, it's about trace gas concentration in the bubbles in ice. So reconstructing the atmospheric composition in the past, and specifically the isotopic composition of CO2. I'll get it there in 1 second. Okay, so this is the record of CO2 that was produced in 1996 and 2006 by the colleagues I worked with in Australia. And it's a very important record for two major reasons. The first one, the site where they got this record from, Low Dawn in Antarctica, is one of the highest accumulation sites in Antarctica. So there is that much snow every year, which means that because of the characteristic that I will explain in a second, you can see events, atmospheric events, that you couldn't see at other sites. Like, for example, this decrease in 1600. This is called the Little Ice Age, this period here. It's where the temperature was decreasing. And we had a very significant decrease in CO2 concentration. So stuff like this can tell you, okay, we had 1 degree Celsius decrease in temperature, we have 10 ppm shift in CO2. It means that the sensitivity of the global on the global scale, it's 10 ppm per degree Celsius. And that's what they use in global models then to run projections and say, okay, if we stop in 50 years, then we should, to emit carbon, then we should get to 4 degrees or whatever. Okay, so this stuff like this is used when you have the temperature change corresponding to that to derive something like the sensitivity CO2 temperature, right? However, the fact that there is a second reason why it's very important this time. This reason being, because of the high accumulation, you can also compare ice measurements, which are in orange here, to contemporary atmospheric measurements. So the measurements done in the last 50 years or so in the atmosphere, which we trust because we know, that is a reliable method. So when you compare these measurements to these measurements, then you see that there is an overlapping, and you can, be safe and say, okay, it's reliable. My measurements are accurate, or something like that. The fact that the temperature, the CO2 decreased when the temperature was decreasing, doesn't tell you though what process caused this decrease. Okay? To tell you something, to try to say something about the process, you look at the isotopes of CO2. Right? When you look at the isotope of CO2 though, okay, you see the big shift decreasing in the delta due to the anthropogenic emission of CO2, which corresponds to the big increase in CO2. However, the record that was published in 1999 didn't have enough points during this period. And that's what we wanted to focus on. And we also wanted to focus on the overlap between ice and firn, which here wasn't done properly. Okay, so what I did, I took samples from a number of, I didn't go to Antarctica, I told you, but we had this collaboration with the Americans and other people. And so a number of samples have been taken from different spots in Antarctica. The red ones are ice cores and all firn, and I'll tell you about firn in a second. And the white one are just atmospheric, direct atmospheric measurements, sites where to perform the concentration of CO2, you measure the concentration of CO2 and the isotopic composition. Okay, so I'll skip this, go very quickly. This is just to make you laugh, but it doesn't work. Okay, so how do you extract air from the ice? You can melt the ice. If you melt, you lose the CO2 because the CO2 is very soluble. A different process is crushing the ice. So it's a dry extraction, okay? If you want to do methane, like CH4 or other compounds, you can melt. If you want to do CO2, you can't melt. You have to extract dry. And that's what we did. We crushed the ice under vacuum, release the air, and then measure, collect cryogenically in a helium compressor, and then measure in a GC and a mass spec. This is what I used to make some tests to show that our extraction was accurate. It's called bubble-free ice. There is no air in this ice that we grow. And because there is no air, we can add air that we know the composition of. So I reference a standard, right? While this is crushed. So you crush some ice with no air. You, before crushing, put your air inside, and then you check that the stuff you measure after the crushing is compatible to what you expect. Third, you already know this. Let me go quickly on this. Because it takes sometimes for the bubbles in the ice to close off, as I say. Here they are closed. Here there is open porosity, so the air can diffuse. Okay? This time I'll give you some carbon-14 modeling. Because of this process of diffusion, the composition of the atmosphere which is trapped in the bubbles is actually not exactly the same as the one in the atmosphere at the time when it was trapped. So what you need to do is to model this diffusion and then correct for the processes that act during this diffusion. And I show you an example of the modeling. This was done again by a Dutch guy, Christoph Beutzer. Very good with MATLAB. Okay, this is the depth. Okay, the first 65 meters, you have diffusion of air. This is the surface. This is the carbon-14 CO2, and that is the year. In the 59, it starts going up in the atmosphere because of the bomb spike. 63, boom, big spike, and it diffuses through the firn, and then it gets trapped here. So the spike the spike was 750 or more, but the recorded signal, it's actually only 600. So there is a smoothing of the atmospheric signals that basically you have to consider when you reconstruct your atmospheric compositions. Okay? So this is what you see in 2000, it's getting there, give it time, in 2012 or whatever, of the bomb pulse of the 1960, right? So it's a completely, not completely, it's a different peak, but it's somehow telling you something about what happened in the atmosphere. You just have to know how to convert this into the one that happened in 1960. Now, carbon-14 is a very good tracer because in 1960 there were already measurements, so we know exactly what happened in the atmosphere. And because we can measure this, what happened now, what we can measure now in the firn, then we know how the firn records the atmosphere. And so we just need to find out how to compare from what. And this is done with this kind of modeling. And there are a number of traces that I used. This was published in the model that works in, paper written by the model that works in CSR in Melbourne. And so basically, because of this diffusion, this process is altering the concentration somehow of your gases in the bubbles, in the ice, in the firn. What you have to do, you have to consider that there is an age distribution when you sample the air out of your bubbles. So basically, out of one layer of ice contains air from maybe 1950, but also some air from 1900 and some air from 1980. Okay, so you have to decompose this signal, as well as there is a delta age, so a difference in age between the ice at one level and the air in the bubbles at the same level. If the ice is, say, 1700 at this level here, then the gas in that layer, same depth, might be 1850, so 150 years younger, or something like that. It depends on the site, it depends on the temperature, accumulation rate, number of. Anyway, you can reconstruct for each site, South Pole, DO8, which is again the site that I was talking about before. And there are corrections that you have to make on your measurements due to the gravity and diffusion. Again, the model can be used to correct for these effects, and the corrections are quite significant, especially for the isotopes. 0.3 per mil is quite significant for us, since we claim that we have a precision of 0.02 or 0.05 at most per mil. However, the maximum uncertainty is quite low, so 0.03. It's a quite precise correction, even though it's a significant one. And the same for diffusion. Depends on the age, but again, the uncertainty is quite low. We can constrain these processes. And that's what Kati did in her PhD thesis in 2000. And she compared the delta 13C measured in the ice, which is the process, to the one measured in the firn. This is ice. This is firn. This is low dome, a very high accumulation site. This is South Pole, a very low accumulation site. However, they should match, but they don't. See, there is a discrepancy of up to 0.2 per mil there. And they had no explanation for it. In 2000, in Kati's thesis, there are 2 pages saying, maybe it's this, but it's unlikely. Maybe it's this, no, it's unlikely. Maybe it's this, no, it's unlikely. So they didn't have an explanation for it. They tried to see if the firn model was creating some problems in this correction that we do. But when you correct model the gravity with the model delta 15N, the delta 15N is a good way of correcting for the gravity because delta 15N is affected mostly by the gravity. So the gravity is affecting the delta 13C. So with the model you can correct the delta 13C. You can correct with the measured delta 15N. As you can see, the difference is very small. So the model is doing a good job. It's not the modeling the problem. There is something there that I didn't know about. And so what I did, I compared a number of grater. I told you about the dry extraction. So the graters are the containers where I extracted the air with the ice, shaking the ice and destroying the ice. And they all matched well. The delta 13C. Focus on this because the CO2 was already was overlapping the firn well, whereas this overlap is a new thing. And I could match also a number of sites, different sites, including South Pole, SP, and DO8, which were the two sites that didn't match before. And most of these is because I did lots of tests to check that the extraction procedure was not affecting the concentration and acidotic composition of the measurement of the CO2. And so what we can now do is we claim that our measurements are reliable. They overlap the firm, which overlaps the direct atmospheric measurements. And we can use the CO2 record and the Del13C record in a double deconvolution. Where is it? KFTD, it's carbon filter double deconvolution. So it's a model that basically takes into account the fluxes of CO2 that can create this kind of trend in CO2 and the causes of this change in the constrained by the Del13C. And so once you take into account in the first plot there, you have the fossil fuel emission and then you change. So the anthropogenic effect on the CO2 concentration in the atmosphere, you can then partition the reservoir sphere and the ocean flux. Okay? And this is just in the pre-industrial. And there are a couple of very interesting points. First of all, both the terrestrial biosphere and the ocean are decreasing. Decreasing meaning sinks of atmospheric CO2. So they are taking up CO2 from the atmosphere. So the more we throw CO2 in the atmosphere, the more the ocean and the terrestrial biosphere pick up CO2 from the atmosphere. So this is of course a very beneficial effect for us, because if this wasn't acting like that, the CO2 concentration was probably, I don't know how, maybe double, yeah, I don't know how much more it was. So basically they pick up 50% more or less of what we emit, and 50% of what we emit stays in the atmosphere. It's more or less like that. This is written in the IPCC, you can trust it. And then there are interesting events, atmospheric events, like this one in the 40s. The ocean picked up lots of CO2 there, 1.5 gigaton. It's quite a significant response. We don't have yet an explanation for that, but it's very important that we have this result now, because before measuring the isotopes of CO2, the modeling that they did used to say this, you can see that the CO2 was going up and then was a bit more flat and then going up again. And the fact that this flat here was attributed from the model to the terrestrial sphere. Now that we have the Del13C, the isotopes, we are actually constraining it better, and we can say, no, it's actually, there is a contribution from the terrestrial sphere, of course, but it's mostly oceanic. And now people are trying to see, and actually I've got collaboration on this, why the ocean responded like this during this period. And one possible hypothesis we are testing is the dust fertilization. There was a big drought, especially in the United States in that period, in the 40s, in the 30s and 40s, and that creates lots of dust. And if it's rich of iron, the dust can fertilize the phytoplankton in the ocean, and the phytoplankton picks up CO2. This is an hypothesis that we are testing with some dust concentration measured in America.
Wouldn't that to do with the Second World War?
Yeah, no, it shouldn't be. If we trust the fossil fuel, the Second World War affected for sure. But if you think about it, were we producing more or less CO2? It's very difficult to say, but we have got some constraint on that. So if we trust that fossil fuel emission scenario there, not scenario, reconstruction, the red line there, then you constrain that well. Maybe there is an uncertainty there, but I had a talk with people that do this kind of reconstruction. They believe that the uncertainty can't explain this kind of stuff. And then going back in time, I told you that we especially wanted to get this Del13C, which I haven't got there yet, but I'll show you in a second. Now I have. This is what I published. Now I've got not published material that I show you in a while. Secret, don't say anybody, top secret. So the model is telling us it's mostly terrestrial biosphere. However, the model is just assuming that the 13C is going up. See how the 13C is going up where there is no bond there? In the 1600?
Yeah.
In the isotopes, in the 13C? So it's just because of the correlation metrics between CO2 and the isotopes, but the model doesn't know, it's not constrained. And that's what we did finally. And this is top secret. I finally measured the 13C in this period with the different color. It was a mess. I'll tell you another day, it's too long. But we've managed it, and we see that when the CO2 is going up, the 13C is actually going up. That's quite significant, and we didn't expect that to be that significant. So we are now more sure that actually this one was a terrestrial biosphere event. So we now are looking up for possible explanation why. So I told you this period was the period called the Little Ice Age, where the temperature was decreasing. Apparently the effect of the temperature on the terrestrial biosphere was quite significant. So we are looking at possible explanation because most of the terrestrial biosphere is in the northern hemisphere. That probably affected more the northern hemisphere, but then the CO2 is mixed up globally, so you see that also in the southern hemisphere. And we have an additional constraint. This is very new stuff. COS is carbonyl sulfide. It's a very ultra trace gas. They measure it at the University of East Anglia. We extracted the sample, they measured it. And you can see there is a peak there. Now, what is COS doing? COS is picked up by the plants through carbonic anhydrase with CO2. However, CO2 is then photosynthesized, whereas COS is hydrolyzed and goes away as H2S. And we know that, Giovanni, you can explain us, that the CO2 is picked up, is also respired by the terrestrial biosphere, whereas COS is only picked up. Okay, so if there is a change in the gross primary production, how much CO2 we found taking up, and there is a corresponding change in the respiration, also the soil, all the terrestrial biosphere, maybe you don't see any change in the CO2 concentration. But because the plants have picked up more CO2 and have picked up more COS, you should actually see a change in COS. So COS is, while CO2 responds to the net primary production, the COS, actually, Giovanni can tell us more about this, COS actually responds only to gross primary production. And actually we are working on this. So this could be a very new biomarker for gross primary production, reconstruction in the past. And this is consistent with our interpretation, because what we are saying is, what we are saying is that the temperature went down, the terrestrial sphere reacted in a way that basically, I have to explain this a bit. The CO2 went down not because they were picking up more CO2, but because they were respiring less. Okay, so there is a dependence on the temperature of the photosynthesis as well as of the respiration. And respiration depends on the temperature more than the photosynthesis. So if there is a 1 degree change in temperature, then it's going down, the temperature is going down. Then the photosynthesis goes down, respiration goes down more. So there is less CO2 in the atmosphere because the balance between the flux goes, in the verse of changing towards, decreasing the CO2 concentration. But actually the COS, because the GPP, the gross primary production, was decreasing during that period, COS is actually increasing. So this makes a lot of sense to us. We can discuss about that. It's not complete. It's not written yet, and it's not completely understood by myself.
Yes, but the dynamics looks different.
I mean, I
see a quite broad peak for OCS in respect to the.
Well, this data have not been collected yet. I must acknowledge that there are big uncertainties there. There is another record done by other people on COS from Antarctica, which also show an increase during that period there. So we are not completely sure yet. We are working on this. If our record and that record match, we need to show that everything is consistent, and then we can say, okay, we are pretty sure that that peak is realistic. It is an atmospheric signal, and then let's see if it makes sense with some kind of modeling that the gross primary production was going down and the ecosystem respiration was going down even more. And so that's all. I just want to tell you that it was quite a what do they say? The English say everything is productive. You need to be productive, right? In Italy, you need to be full when you eat. Productive, maybe. Productive, that's a different concept for us. So we were very productive. We have lots of collaboration now that I hope we can develop in the future. And I finally turned into the first Danish kangaroo. And that's all. Thank you.
said COS is ultra trace, you extract it and you measure the concentration. Can you measure the isotopic composition of COS?
People in University of East Anglia are trying to do that.
Yeah.
It's not that easy. So we are talking about COS is not, the CO2 is 400 ppm right now. COS is 400 ppt. Not ppb, ppt. So tend to, it's almost a regular isotope. So measuring the isotope of that, it's not that easy, especially because they measure lots of different compounds, different ultra trace gases, and so they don't have high precision on each one. Their power is to measure a lot of them, which they can use them to do comparison. So
It's not
probably the
optimized
technique
for
they use, it's a GCMS, and it's not, can't be used to do isotopes. Maybe in a different way you could, possibly, I think you could.
Just a consideration on that, because I can see well what you are saying, that maybe the respiration is less, but I will think more about the microbial, not the vegetation, because we have so many reconstruction of productivity in the lithalization with the tree rings, and on the vegetation they will not react like that when the temperature is very low. They can reduce the photosynthesis, they reduce everything. So they reduce the period of growing, they will reduce the productivity, but everything will be in equilibrium. Maybe the microbial.
It is possible. It's a long period where the CO2, it was 280 ppm, then it gets down to a minimum, and then it stabilizes to around 275 for almost 200 years. And then it kicks in the Industrial Revolution. So somebody told me to be such a long period, I think it's the soil, it's not the interested by speed, but it's difficult to say. We'll try to model this tool. We are still, we are now, I produced this data in May. Just before I was like working like crazy. So we'll see.
Have you tried to quantify the correlation between the two sets of data? Carbon dioxide
In
and
terms of
the correlation. No, the correlation between carbon dioxide concentration and the delta C13.
Correlation.
The correlation, just put the linear tool.
What?
You mean the plot, CO2 versus
Between the two.
I haven't done that.
Just, okay. Because this might be useful to understand better.
Sure,
this.
yeah. It's not,
And what is the amount of increase for the delta C13? Because I can't see the scale on the right.
it's more or less, depends where you, this is
the
the top,
peak,
the big
that's right,
yeah?
the top.
Do you compare to this or do you compare to this? The maximum here it's about 0.1 per minute. It's a small one. Look, one thing is to see this kind of things. But when you go with this is 7 ppm.
Okay, and in terms of isotope rates,
It's 0.1 per minute, something like that.
1 per minute.
0.1.
0.1. Okay.
So you need high precision there to look at this variation, and that's why it's the first time it's done. There are people working on different core in Antarctica. It's called WACE. They are Americans, and they already reconstructed that. But the CO2 was higher than the one we measured, and we believe it's in situ production. And so if there is in situ production, if there is CO2 produced in the bubbles, then the isotopic composition is altered too, depending where the CO2 in the bubbles is coming from. If it's organic, if it's carbonate.
And how many samples have contributed to that value, to the peak? I mean, how many samples? Just one sample. This is just one data point. I will check it.
Look at the trend. Look at this 1, 2, 3, 4, 5 samples. They are within 0.02. We believe this is very high precision. We have some, I agree with you. It's only 1 point. You can't have more than 1 point in the same spot. We can do that to measure CO2 isotopes and the COS and other compounds. We use the whole core. We didn't have enough ice to do more, replicates.
Okay.
You would have to go there and drill another core. You can measure very close, but you can't measure the same piece of ice.
How long was legalizing? 100 years?
No, more, 400.
400.
Nobody, it's just a rough, You have to think about, we are in the interglacial, it's a warm period now, but the temperature is decreasing actually. It was Now it's increasing because of us. But in the last 10,000 years, so it peaked 10,000 years ago at the beginning of the Holocene, and then it was decreasing. With some variation, of course, up and down. But on average, it was decreasing. And then the Industrial Revolution changed everything. And now it's, I think the difference is 0.8 of the degree between 1950 and now, something like that. So it's quite up. And it's measured and everybody knows that.